Yeah, June 12th. Welcome. You want to lead? You want to lead the meeting still, Lindsay?
Oh, go for it, Dom.
Oh well, I don't know what are we talking about. So
okay, fair enough. Yeah, I mean, so picking up a bit from last week, I guess, going through the RFG presentations, and I think Mike has a poster. So if you guys want to chat through those, we certainly can. And then if there's a bit of time, we can go over some of the updates to GeoAnna and how SimPEG is going to start relying on GeoAnna, at least for sources. And we can chat sort of about a trajectory for that.
Okay, sounds good. So RFG first. Thibault, you wanna kick it off, or you want me to do it?
Both way works. Give me a.
Okay, 1 second. We're just gonna screen share here.
Yeah.
You see this? Lindsay to infinity.
Yes, the infinite loop.
Okay, let's just go to RFG.
Oh, I can share my screen with the presentation. That works too.
It's up to you, man. I see yours anyway, right? You are making most of knowledge. This guy.
Yep.
Perfect. Here you go. You can drive.
Let's just put a timer so I got an ID. Like I was still putting slide yesterday, so it would be nice to have like a first time thing.
You want me to talk?
Yeah. Yeah, I can definitely like try to do like a talk thing.
Is your talk 15 minutes, Thibault? How long
It's 12 minutes and 3 minutes of question.
Okay.
So 15 in total, but 12 minutes recommended for the talk.
Okay.
So hi everybody. So for my talk today, we're gonna look at how you can make the most out of your knowledge, and so we're gonna use a bit of machine learning to make geophysical inversion more geologic. And first of all, just want to say that all this work is done in the SimPEG framework, like the open source software that my colleague Dominic just presented before me. And our objective during this talk, it's a big one. We're gonna try to tie together geophysical, petrophysical, and geological information into a single geophysical inversion framework. And to show you the work we have done on to that purpose, I think the best way here will be to walk through an example. So we're gonna base we're gonna base our presentation on the TKC example, which is a diamantiferous kimberlite in the Northwest Territory that have been quite well studied both geologically and have also a lot of geophysical article published on that one. I've put one reference here for a study done on the potential field section, as this is the technique we're going to use today through this talk to illustrate our work. So first of all, like a presentation of the setup and state of the art for the potential field inversion. So based on the petrophysics of the site and geological knowledge based on drilling, we have created this synthetic model. And so at the end of the day, for potential field, it ends up being a 3-unit problem. So we have the host of background, which is have a density contrast and magneticity contrast of just 0. Then the PK and VK units are not distinguishable, and both have the same physical property with a very low density contrast and a weak magnetic susceptibility. And then we have this dipping HK unit, which has a lower density than the background, but not as strong as the PK and VK, and a very strong magnetic susceptibility. And from this model, we're able to forward gravity and magnetic data. And usually, when we have this type of gravity and magnetic data, we use our favorite inversion code, SimPEG, UBC code, some in-house software you have, and we get a gravity and magnetic inverted model, so separate model. And that's what we get at the end of the day in this case, for example. So you see here that like here we have the outline of the two bodies, and we see that for the usual smooth inversion we're doing, we cannot distinguish even that if there is two bodies. We definitely see there is something there, and we have a bit of the outline, but not much. And so how this code works usually is through the minimization of an objective function, which is a sum of a data misfit and a regularizer, and the regularizer usually have like two parts, a smallness and a smoothness. And the smallness term here, which like basically try to keep things close to a reference model, is what we're gonna concentrate on today. So a very important thing we see here is that definitely the recovered model doesn't fit the petrophysical knowledge we have on it. For example, so here we represent the petrophysical data as a sum of Gaussian. So here we can see like a cross plot of the different units. So with the background HK and PK, VK. So that's the petrophysical distribution we have for this unit. And if I plot the smooth inversion, we definitely don't recover that distribution at all. So our first goal will be to try to recover a non-distributed petrophysical distribution into our inversion. And turns out that we can do that through the smallness term by updating the reference model and the smallness weight at each iteration based on a new physical property distribution that we learn at each iteration, which is basically an average of our prior distribution that we input and what we see in the recovered model. So you see here an animation, for example, on how we update the reference model to get closer and closer to the distribution, petrophysical distribution that we input. So, okay, let's try that for our TKC example. Again, we have the gravity data, and now we also have, as an input, have a density distribution. And same for the magnetic, we have the magnetic data and the magnetic susceptibility distribution. And so we recovered a much more clustered inversion result, but still it doesn't quite fit together. Like we get a bit of the PK, VK unit here, but then we get this halo, and the mag inversion just recovers the PK, VK unit, and we don't have any signature of HK. And when we look at the cross plot, well, it's clustered. We have recovered some of the value, but definitely when we put the two together, it still doesn't match. So our solution now, well, we can tie both inversion through the petrophysics into a joint scheme. So that we can do that through SimPEG, which can handle multi-physics inversion. So now we're gonna and now this is a much more dramatic improvement that we do. Like we recover a single geological model from the inversion, and we can now we can distinguish between PK, VK, and the HK unit, and that we were not able to recover through the smooth or the singly petrophysically constrained inversion before. And we recover much better our input petrophysical distribution. But still, okay, now we're able to recover the petrophysics. But what if I can add some geological information? For example, if I had like even a single borehole and I have a log of it, not even geophysical borehole geophysics, just the straight log, so you can constrain directly on the geological model, and we add that to our inversion and to our classification. So that's what we did, and now see that we have the trace of the borehole here, and see that we can definitely much better constrain with a single borehole the depths of the HK unit and still recover the petrophysic. And in the 3D, you see that we have a better sense also of the deep of this HK unit. I still miss the slide for the summary of TKC. Okay, and so that's the stage we're at, and so you see that I think we've done a very good job with the petrophysic, and you see how we saw how we can include geological information, for example, through a borehole and just adding a log into the geological classification. But actually, we can do much more complex classification. And that's what we are working on these days. So we have, for example, a time domain example that we linked to with our framework for petrophysically constrained. And in this framework, like what we in this example, what we said, for example, is that we impose that we need to recover a resistive layer between two conductive layers. So it's not something that the time domain data are very sensitive to, but if that's a geological knowledge that you have about your area, you can include that into your inversion to have like to have something that's both fit your geological and geophysical knowledge. This is a bit of a silly example, but I kind of like it to show you how that we can do very funny things with that. This is a DC inversion example with just two spheres, and here we can impose that when we do the inversion, that the resistive unit cannot touch the background. So the inversion just put a layer of the conductive things around. Not very geologic on that side, but it shows you a bit like the different kind of complex classification that we can do. Oh, this one is a time domain example more in the hydrogeophysic example, where, for example, if you have boreholes around and you have done some kriging of a simulation of your interface between like a dry, fresh, and salt water, this is the type of work you can also include into the inversion to try to constrain on where the interface will be. Some funny stuff here that even like we show that you can even have very complex relationship between your units with like quadratic, cubic, or single point relationship between your different units. And I'd like to just finish on a word about the SimPEG framework. So all the work we've done, like on updating the reference models, the petrophysical model, etc., all of that actually happens in that single regularization package. And that's actually very powerful because that means that whatever we develop in that package, we can link it to any survey that's developed into the SimPEG framework. And that's how we were able to, by coding it just once, to link it to gravity, MAG, a time domain EM, or DC. And we have other example with MT or frequency domain EM methods. So that's a very, very powerful thing to do. And as we said, like the SimPEG package can handle multi-physics, so we can jointly invert any methods together. And another point that is very powerful with that framework is that it's an open source. So our goal is to release this code to the community and also release a case study and example. So everything is going to be reproducible and you can run it on your own machine or use this code later on. Thank you. 12 minutes and 30 seconds.
Oh, wow.
Okay.
I like your crosscut histograms on the axis. It's really good.
Yeah.
That's cool. That's good. work hard.
Yes.
One thing I was going to ask, so you have some plots with magnetic susceptibility models.
Speak louder for the mic.
Yeah, so the plots that you had for the mag sus models, I'm wondering if you tried plotting it on a log scale, or did you want both of them on a linear scale? Like, it's maybe nitpicky, but did you try plotting it on a log scale and see what it looked like?
I did try to plot it on the log scale. So two things. First, the background is 0, so you have to add something, like a little bit something, to be able to plot it on the log scale. And how small is that can really stretch a thing, can really stretch the log scale.
Right.
And at the end of the day, what happens is that in the log scale, the PK, VK unit and the HK unit doesn't look that different because they are like
Way above 0.
like there is like a factor 5 between the two.
Okay.
It's not even an order of magnitude, just a factor 5, so they look very close to each other. While in the linear scale, yes, there is still a factor 5.
Yeah, fair enough.
So and it's a linear problem, so like the data react linearly to your input, so I prefer to include that to do a linear plot of this property.
Yeah, okay.
Any question from the online participants?
Online. Thibault, I think that looks really good. I'm going to actually be in about noon, so there's a few things maybe that we could talk about. But I think in general, you could basically spend almost all of your time on the gravity and the magnetics. And the TKC example. There's a few things that went by pretty quickly, and just spending a little bit more time on them. First of all, there was that movie that you showed with respect to the convergence. Yeah, that guy there. So there's a lot of stuff happening on the right-hand side, which is changing. And that's going to distract people, and so you're going to have to, try to decide what to say about what's going on there, I think. And then also, I thought earlier on, just when you introduced the first Gaussian slide, where is that? 6? Yeah. So in this one in here. Could use more, kind of introduction. I mean, there's a lot of stuff now that is actually going on with respect to, like, okay, you actually, you have physical property data. This is what the density, distribution looks like, and here's the magnetic susceptibility, and you can do those cross plots, and then you end up with stuff in there. So I think the reader or the listener is just going to have to be, kind of walk through those things, and I think they're really important. So it would be good just to, make sure that they're really kind of on board with that. And then when you started the borehole work, that also went pretty quickly. And I think there's a few more things, like, for instance, where actually is the borehole? What is the information that you're getting out of it?
We can see it because I put the borehole. I noticed that after the inversion that I put it through the very thinnest part of the unit, so you can actually see the trace in the geological model, like in the middle. So I thought I would let it like that for now, but I can maybe. Yeah,
would you be able to, well, I don't know, maybe even just extract that and have a geologic log that kind of coincides with that, but it's outside and shows, okay, I've got background here, I've got PK or a PK, and then here I've got HK, or just something to really establish you've got a length of drill, and then you've got certain rock units that are there, and then this is how you're putting them in.
Yeah, actually there is even more going on in this example. That I didn't have the time to go through right now, but actually, like I have the borehole, so that's an observation. So it's pretty much fixed around the borehole. But what I did too is that around the borehole, depending on how on the distance, it's saying that if you have a cell right beside the borehole and that we have observed HK right beside it, then increase the probability of having HK in that cell. So I actually have like a different weighting around a different proportion weight in my mixture around the borehole to just like say that if I observed here, it's no longer an independent observation on the side.
I don't think you'd need to go into that level of detail.
Yeah.
But just really highlighting, like, okay, I got a drill hole here, and what I'm seeing are geologic units. So they're at a particular depth, and so the log that you've just added, that's looking good. And then just say, okay, I'm able to incorporate that information in, and this is the difference that I get, and then to concentrate on, the clustering diagrams that you've got, the physical properties. I think just really emphasizing this section is really good, would make an impact, and then following this up with the SimPEG slide, I think would be really quite appropriate. And then if you want to end off, pick up on the final example that you've done here and say, well, look, this is kind of a first pass. We're actually doing a whole bunch of other things, and then just to kind of summarize a few of the highlights there with maybe a couple of icons, which you don't have to explain really at all, and just say that we're proceeding with more advanced versions. I think that would be kind of the right flavor. If you talk too much about these other things, I think the impact that you've made, which is really important, then tends to disappear because now their attention is on other items. And I think you do better by presenting less on that final aspect.
Okay, so maybe just keep maybe this different example, just having them like on
as a bullet,
as a in one slide saying, and we're able to do
airborne EM, FEM, TEM, DC,
yeah,
that's fine.
Okay.
So collapse 17 and 20 all in somehow.
All in one.
Yeah.
Yeah, that works.
Yeah, that was going to be my main comment as well. I think that building out the TKC example has a lot of impact, and I think it's worth spending some time orienting people with what's going on. Like slide 9, actually slides, sorry, I'm just 7 through 9 blew through really quickly. And so if people didn't catch all of those pieces, the impact will be lost. So I wouldn't be afraid to spend some time on there and talk about the different pieces of your smallness, where things are going. So can you go back to slide 9?
Yeah, I think I around slide 7, I just look at the time, and I started slide 7 and already 5 minutes had passed. And so I think I don't know if it was. So I think from your comment, doesn't seem I need to cut out the introduction, but cut out at the end. But basically when I realized that at slide 7, I had 7 minutes left, I started to rush a bit more into this slide. I agree.
Yeah, because this is an important slide, and you're explaining here the bulk of what's going on, and then taking the time to walk through the TKC example, and then, as Doug was saying, just bullet points for the what's next. Because right now, those are sort of just disparate examples. And so they might not really connect with people if they don't already have some stuff in mind. So I think it's much more powerful to leave them with the TKC as being the big thing.
Okay.
Sounds good. Any last comment for Thibaut?
Yeah, that looks good, Thibault. That's going to be great.
Thanks, Doug. Beautiful.
And your plots are beautiful, by the way.
Thank you. Yeah, really, I really like those. It's really makes it intuitive. Good job. Mike, is your poster on the...
It should be in the drive, yeah. It's
Nice.
not, it's more of a draft still at this point, but there's kind of at least a skeleton there.
Shoot.
There we go. So I'm not convinced I'm like really happy with kind of the flow of it yet, but so like the kind of general directions that they gave for the posters kind of indicated that they wanted you to kind of have all the same parts you would have in kind of a paper. So they really wanted you to kind of like summarize the abstract. So I kind of tried to do that as succinctly as I could, kind of up here, and just kind of give a rundown of what the whole poster was about. So just kind of walking them through the fact that we're working in one of these underground environments in one of these tunnels. And because of kind of the geometry afforded to us by the tunnel, we have a very limited number of places where we can put our transmitters and receivers. And those really impact kind of our final, like our resolution of our inversion model. And then I kind of just indicate here that we're going to focus on two main problems with resolution, or two non-uniqueness issues that we were encountering. The first of those is kind of figuring out where the target is around the tunnel. And that's kind of what these plots over here are addressing. And then the second one is kind of developing an estimate for how far we think the target actually lies away from the tunnel. And that's kind of what these plots here show. And so I guess when you look at just our standard linear array of electrodes going down a straight section of tunnel, so here we just have like this one single line of electrodes going down the ceiling of our tunnel. If our target sits out here to the side of the tunnel with that single linear array, we can figure out kind of where the target lies along the tunnel, but it basically puts the target kind of wherever the electrodes are and wherever you have that higher sensitivity. So it's saying that in the X direction, our target is centered here at about 25 meters. So it's kind of defining that nicely, but it's telling us that it's above the tunnel when really it's off to the side. So then I guess our solution to these basic problems that we're encountering with this single linear array of electrodes is to build into this kind of ring array where we have kind of one electrode in each face of the tunnel. And we're collecting just like a number of different dipole-dipole measurements that are using electrodes in various rings. So we're getting more, I guess we're doing a better job of measuring like multiple components of the E field. We're not just measuring kind of that X component, and we're getting like a nice variety of like short offset measurements, which are hopefully helping us better constrain like the near tunnel part of the model, and we're getting some nice, like reasonably far offsets too, which are allowing us to kind of sample when the target gets further away from the tunnel.
How many electrodes are used in both sides? When you define the ring.
So it's at least one electrode in each face of the tunnel. That might depend on, yeah. So like here, we can probably zoom in a little bit. So I guess that would kind of depend somewhat on how big your how big your tunnel is. So it's probably more clear. I don't know why it's not showing up there. Huh. I'll have to go back and look and see why that's not plotting in that one. So that's kind of what it would look like in cross section. So we kind of just have one electrode centered in each face of the tunnel.
That's cool.
And then we just kind of have a line of those guys kind of going down the tunnel, along the tunnel. And so while these ring arrays like do really help us kind of address these two main problems that we're seeing. So here you can see this was just with the single linear array. And again, we're placing it above the tunnel instead of off to the side. If we go to kind of, if we put basically one of these linear arrays down each face, but collect them each as like a single 2D data set, but invert them all together, it's still like it tells us that it is actually on this side of the tunnel now. So it is definitely helping, but our target is still like really kind of glued to the edge of the tunnel. You're not getting any sense of how far it is away. And so like when you start to do the ring arrays and you're really kind of getting kind of those diagonal and ring to ring measurements where you're starting to get some of those extra components, you can see that it does want to start to pull away from the tunnel a little bit. So that starts to help with that. And then that's maybe even a little more obvious, hopefully, when we look at this guy where we just kind of slowly move the block further away from the tunnel. And so with the single linear array, it's always kind of glued to the tunnel. Just kind of smears it more, and like that, the amplitude of your recovered anomaly kind of decreases as you get further away, just because the signal you're measuring is weaker. And then kind of same thing when we have the one linear array down each face, we still don't really have any good way of estimating how far that block is away from the tunnel. But as we start to go in and use the ring array, it does start to kind of pull it away a little bit. I mean, we still have a ways to go. Like we're still not really nailing it, but we're definitely doing a little better. And then this bottom one here is kind of showing what I'm gonna try to talk about a little bit. We need to go out further even, don't we? In the middle section where, so I mean, the main drawback of these ring arrays is that you basically multiply the number of electrodes you have by 4. You do it. So the number of like possible transmitter and receiver combinations just explodes. So there's a ton of data you can now all of a sudden collect. But I've gone through, and this part I'm talking about here just really focuses on how we're selecting the transmitters. And so we can, when we're selecting the transmitters, basically what I do is I've just kind of defined like a region of interest. So like, let's say I'm going to have to try to figure, I need to try to make some figures to kind of illustrate this. At this point, I just have the text in there, but I want to try to make a couple of figures that kind of walk you through that a little bit more easily. And so in this case, I've just kind of, like I've defined my region of interest as like this kind of central region here. And I think it goes out like, I think it sits here and then goes out about 20 or 30 meters in the vertical direction. So it basically encompasses like this whole central region. And so I break up that region of interest into basically like 10 meter by 10 meter cubes. And then I basically walk. So I take one of those cubes and I set that cube to what I think my target conductivity might be. And I forward model my data for that cube. And then basically what I've done, I looked at a whole bunch of different metrics, but the one that worked the best, I thought, was looking at like secondary charge buildups on that block for each transmitter. So after I've forward modeled the response of that one block for every transmitter, I basically look at the accumulated charges, and based on those accumulated charges, I kind of try to pick the transmitters which are doing the best job of kind of exciting the block in that particular location of my region of interest. And then I just kind of move that block through my region of interest, all those possible kind of locations that I've divided it up into. And I slowly kind of build up my survey by saying, okay, if I'm taking the 2 best transmitters for each of these blocks, then like what kind of a survey would that give us? And I try to kind of build up that survey like reasonably symmetrically, because you don't want to. Well, if you don't build it up symmetrically, you're going to be prone to getting some of these artifacts in regions where you have like significantly higher sensitivity, and you're sampling that portion of the model much better than other parts of it. So then structure preferentially gets pulled there. So unless you're going to try to do like some fancy type of weighting to try to account for those differences, it's really, in the situation, it's really advantageous to try to keep things like reasonably symmetric.
Do you do any type of sensitivity weighting, or is that too risky in that type of setting?
Well, I mean, even in these small problems, it's just really not even feasible.
Yeah.
Because, I mean, model size, since we're using an octree model, our model can be reasonably small. But, I mean, with this one, I think there's like, I should write down the exact statistics for the number of data and the number of transmitters are in each one of them. But I think the full like comprehensive dipole data set has like just over 600 transmitters and probably over 100,000 data. How many electrodes is that? That would be, I think we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 11, so like 44 electrodes in the full ring array then.
Okay.
So as far as like, there's definitely, that's no problem for most of the systems they have today to lay out a spread with just 44 electrodes hooked up. So, but I guess kind of the exciting thing is that we see when we kind of choose our transmitters in these different ways. This plot here just kind of is showing kind of the norm of the difference between kind of my recovered model and my true model for some of these different surveys that I've selected. And so the surveys along here, surveys 1 through 5, are just kind of these surveys that I've slowly built up. So they have like incrementally larger numbers of transmitters. So in the first one, I'm just taking like, I think that one's based off of just taking the best transmitter for kind of each of these block locations, or maybe the best 2 transmitters. And so that's only has like 30 to 40 transmitters out of the 600 and some possible ones. And you can see that as far as the kind of the norm of the difference between the models, just with just that very small subset of our transmitters that we've kind of chosen carefully, we can get basically the same, we get a very comparable model that has very similar resolution to using all of those data. Because this one here is just like, this is kind of the norm of the difference between our true model and our recovered model with the single linear array. This is the one with the 4 linear arrays, and then this is the full ring array. And then these are just some of the ones with the different metrics that I was trying, but the charge ones, it's kind of right down here. So we can use like somewhere between 5 and 10% of the total transmitters, and like our recovered model is very comparable. So even though there's a lot of data there to choose from, we really kind of only need a very small subset of it that's kind of chosen carefully in order to get most of our improvement in resolution. And I haven't really decided if I want to go into it or if I want to show it. I would need another picture here, but this is kind of trying to tie things back in with the Mosaic case study where we kind of had this like horseshoe-like shape of tunnel. So over here, I've kind of simulated that. So this would basically be a slice that's looking this way, kind of through that horseshoe. So you just get the like, cross section of the tunnel here and the cross section of the tunnel here, kind of in this diagram. And if I've set like a little conductive anomaly kind of right in the middle of that horseshoe, even with the single linear array of electrodes kind of going around the inside of that horseshoe, I can do kind of a reasonably, I mean, it kind of shows you that something is sitting there. But then if you shift the position of that guy, either kind of above or below your kind of electrode plane with the single linear array or the kind of 4 linear arrays, it's always putting your recovered target kind of right on that main plane of your data. And if you move to the ring arrays, you can start to get that pulled up to actually be showing you, no, it's actually sitting above my plane of electrodes. So that just kind of, yeah.
I really like that figures. I think it's pretty dramatic that you can definitely see the difference between your linear and ring array.
Yeah. I do need to remake some of these figures too, because this was done, this is a slightly older run, so I definitely need to make sure I go through it and check and make sure that nothing's going to change with that. I don't think it should. None of the other ones changed too dramatically when I reran them. So
let me just check at the other result, but I don't know, but I do find this figure is even more dramatic than the other one.
in some ways, yeah. Yeah.
Do you think by, say, or I guess it's pretty, depending on how deep it is, if you put some surface electrodes too, with measuring like a horseshoe, you would tighten up that anomaly a little bit?
You might be able to. Yeah, in this particular case, we were about 1 kilometer underground, so that wasn't really very feasible. But
I guess I was just asking, do you think adding more electrodes would tighten up the anomaly? Because now you're being able to detect where it is.
Yeah.
Would adding more electrodes be the case, or?
So I mean, another.
At least electrode positions, I guess, different areas.
Yeah. So I think getting electrodes off of that main plane.
Yeah.
And getting some interesting like measurements that are kind of crossing that and capturing some different components of the field are really valuable. I didn't want to get into it too much here, but in the paper that I'm going to put out, that all this stuff is going to be included in, I also kind of talk a little bit about some off-tunnel boreholes and kind of go into that and kind of show how you can use a select few of those to really kind of improve things and help tie things down too. But like, there's already a lot to try to show in this little poster, so I didn't want to try to complicate things further by adding those off-tunnel boreholes at this point too. I don't know. I'm open to suggestions on that too, if you guys think that might be useful. For these, well, for defining the around tunnel location of it, those off-tunnel boreholes didn't really have any impact because we were already doing a pretty good job with just the ring array. We didn't really necessarily need the off-tunnel boreholes. They do help when we're trying to really define the location or the distance of the target away from the tunnel. The further it gets away from the tunnel, kind of the more some of those off-tunnel boreholes help. And I would have to go back and look at some of the results, but I think I ran a trial with this horseshoe type geometry too, and it definitely did help to tighten things up nicely. So there is definitely promise there, but it's, I mean, those are definitely, it's going to be expensive to drill them to start with. And then the question of where should you actually be putting them is kind of another whole thing that you could go through trying to kind of optimize. Yeah. At this point, I've just kind of, in this straight tunnel section, I kind of placed them right on the edge of the region of interest, because in this salt mine example where you're worried about these water-bearing regions, you definitely don't want to drill into one of these water-bearing regions either. So if you had an area where you were worried about the water, you wouldn't want to be trying to drill holes in there necessarily until you had checked it out a little bit. So my thought was just put like a couple of them kind of right on the edges of our region of interest and see how those can help us tighten up the stuff right in the region of interest. It's kind of what I did with those. So as an overall plan, I think I would definitely, if somebody was going out and going to do this, I might recommend that they just kind of start out with some kind of reconnaissance to kind of define their region of interest. So maybe just start with the single linear array, because that's going to do a decent job of telling you where along the tunnel you may have things that you need to worry about. And then as soon as you kind of have defined that, if you really want to know kind of where it is around your tunnel, you would probably want to kind of branch out into the ring array and target it in that area. And then if you feel like you still need more, then you might consider adding some boreholes after that. Just slowly build into it, I guess. Would kind of be my recommendation for that.
Hey, Mike, we're starting to get a little closer to 11. So do you mind if we maybe focus conversation just on like getting some feedback on the current poster? I know there's a whole bunch of interesting questions we could spend time on.
Yeah, absolutely.
Is that okay?
Yeah.
Okay.
Can I add a few comments?
Yeah.
Okay. So I kind of think from the presentation of your poster, I'd suggest rearranging things
Sure,
a little bit. So the first part, your introduction and your abstract, that could be a first column. Try to reduce the number of words as much as possible. For the, then, so in that first column, you want to sort of start to introduce the non-uniqueness, which could really be the major thing in the second column.
Yeah.
So I think having some really nice examples, that just showed you if you had a linear array, then you get conductivity all around the tunnel, and yeah, I think you don't need to have like very many scenarios of these, but maybe something, maybe in in a cross-section view as well as in 3D, just to really make it completely obvious if somebody is looking at it, like, oh, there's just a ring of conductivities around that tunnel with the linear array.
Yep.
And then to have some kind of a cartoon that tells you something about how if you have different locations of your conductor, or if you have a conductor at a particular place, but you've got different currents that are going, they're going to actually ignite that that sphere differently. I mean, just to get across that sort of general concept, and then to just show an example with then a ring array. Okay, because so that would the sphere that is ignited by 4 different electrodes. Okay, you're going to have a different response. So then you just have like one example with a linear or with a circular array, and yeah, now you just see something that's entirely different. So I think that's kind of all you need to really make that impact, and then that might slop over a little bit into the third column or not, but then the third column could be, okay, what do I do for reducing the number of electrodes that I'm going to be dealing with? And yeah, just showing some way how you could potentially reduce that number, and that you get a result out that is actually similar to what you had in the second column with the ring array giving you, but done with, a 1/100th of the total transmitters or something like that. And then you have a conclusion just saying that, this work is, this is a major advancement in how to think about illuminating bodies and finding them in 3D, and work is still progressing, or something positive and impactful.
Yep.
For conclusion. I think that would be good, and you want to make it so that the poster is almost self-explanatory to somebody coming by, right? Yep. So if you have to spend a lot of time kind of looking at details of images and showing that, yeah, this one's different from this one, And if you look carefully, you can see it's not quite as yellow right near the tunnel. That gets to be pretty intricate from a point of view of a poster. So just try to elevate it up, be as simple as possible and as self-explanatory as possible.
So maybe don't focus so much on this distance from the tunnel component of it.
Yeah, that's a question somebody can ask. How big an effect is that?
So maybe just kind of focus in on this top panel here and the third one down with the
I'm not sure if there's anything else that can accompany that, just to show how to really kind of get a sense of the 3D image of what's going on underneath the Earth.
Yeah, no, I'm sure I could make an isosurface plot of some sort that would visualize that a little nicer in 3D.
One other diagram that could be helpful, and I don't know if you've got something like this or how challenging it would be to put it together, but if you have a simple diagram of a small section of tunnel and just giving the reader like a bit of an idea of how the different electrodes are connected. So like the difference between your 4 linear arrays versus the ring array. So even if you had 2 rings of electrodes and just a sketch of a little wire path just to show the difference between those. Because you're spending a lot of time looking at these different geometries. So it's really important that people understand sort of what that looks like.
Yeah.
So even, because that could be a really nice sort of lead up in the intro when you're just talking about these different survey geometries. Yeah,
I do have, when I kind of go through and select the transmitters, I definitely do have ways that I can make plots that are kind of, it just shows the electrode locations and then basically lines connecting the 2 poles of your transmitter. And so I could easily plot up sets of those.
Yeah, and I don't think you would need too many, but just enough to make sure that everybody understands the gist of the geometry.
Yeah.
Alrighty, is that it for everybody? Let us. Should we cut it here, or do you want to do this?
Dom,
talk, Dom.
Yeah, let's go through yours.
Okay, I'm not gonna go through the details, but
So we want the full unedited version here, right? We're like the audience.
That's gonna be at the conference. I just followed your suggestions, guys, and added more context for the problem. So right up front, the case study, the Kivitsa, and then talk generally what was the general approach, that we have different codes at UBC. We're from UBC GF, wrote a lot of very important piece of softwares over the years that do individual modeling of all those properties, and then pulled your slide from the burrs, saying that doing this technology takes time and lots of efforts, and it's not really easy for anybody to come in and work with it. And that's why that's where kind of SimPEG fits in, is to be able to bring together all these methods within one framework. Then go to the framework. What is it? You guys see these slides last week. So what is open source? We need pictures, right? So pictures of everybody, and then what is a framework? How does roughly it works? Forward simulation, what it can do, be able to see fields, proceed with inversions, so go from data to model, and then it's in Python, so we can leverage a lot of the stack of the ecosystem. And then back to geophysics, so where we're saying that we're bringing together all the different methods. That's the goal, so that we can model it all either separately or jointly or cooperatively, since they're all in the same umbrella. And then it's going to be the Kivitsa back same slide, but now looking at the data, I'll get a little spiel of what's in it, what we're expecting. So first, we could do forward modeling. So if we do simulations, we'd be interested at seeing what kind of fields is happening where, what kind of response we're expecting. So this is for the DC. Stole it from Soggy. This is magnetics, presence of remnants, blah, blah, blah. Gravity, look nice. So it starts to look a lot like the real data. And then we can invert them all to get the physical property distribution. Showcase the new octree because we're very proud of it. So we can invert all the mag grav on the octree meshes. And then this is a 2D inversion for DC. And then what's next? Large scale, parallelized, and then introduce Thibault stocks. We're gonna start doing joint methods for the potential fields. And then finish with comments, links, go see the site, that type of stuff. That's it. Comments?
That's great, Dom. Dom, that's really good.
Okay, sweet.
That's really nice.
Those are beautiful slides.
Yeah.
Yeah, lots of not much text. I'm following the Google, the new Google advice. 2 words max. No, but
That's great.
okay, sweet. Lindsay, you want to finish off with the? Let me kick off here. Stop sharing. You want to talk about Joanna before we finish?
I'll give the 1-minute version.
Perfect.
There is a pull request on Joanna. I think the link is in the blog from this week. And so Joanna is going to be where we store analytics. It's meant to be like a very object-oriented approach to analytics. And so when we think about building the solution for a dipole in a whole space, let's think about a mag dipole in a whole space. Magnetostatic. So there's a few different properties you can set. You can set the permeability. If it's a loop, we can set the radius. We can set the orientation and all of those kinds of things. And so those are going to be actually like properties of the analytic solution. So that the idea is that you create sort of everything that defines a dipole in a whole space. And then you can ask different things of that object. Like, what is the vector potential at these observation locations? What is the magnetic field at these observation locations? So that's sort of the idea. There's an example that's in the pull request, so you can take a look and sort of see if you understand what I mean by like this style of object-oriented approach, and see if this fits with people's mental models. Because it is a little different, but I think what's exciting about thinking about things like this is then hooking up widgets. I think we can be smart about how we do that, and like basically tracking the state of the object and being able to tie a visualization piece to that. I think down the road could be quite powerful. But for now, oh yeah, thanks, John. Then so if somebody's willing to take a look and do a quick read through on some of these additions, I added a bunch of docs. So that's actually a good place to start, is just build the documentation locally and poke around in it.
So the analytics are basically a self-contained problem with a survey and everything. Is that, am I understanding it right?
Basically, because it is like, to think about a dipole in a whole space, we define the model, we define where the source is, and then the only sort of input that we provide as an input to methods is then where you want to look at the thing or where you want to evaluate it.
Yeah, that's great. Sweet.
Yeah, so eventually SimPEG will start relying on this for sources, as well as for like comparisons with analytics and things like that.